Hello everybody. This is the second lecture of week 11. We're going to conclude the topic on tests, hypothesis tests. Today we're going to look at tests on proportions, starting with single sample proportions and then going to two population or two sample proportions, and then finally we'll finish with tests on variances. Okay, as we saw with confidence intervals, a test on the proportion will make use of the normal approximation to the binomial. And this basically requires that NP is approximately greater than 5 and NQ is approximately greater than 5. And basically it just means that the N and P values are selected such that we're not too close to either end of the distribution of the binomial. A binomial distribution must be between 0 and n successes and n trials. So the normal approximation to that, if you're too close to either end, will extend beyond the endpoints and result in an error. Note that there is one difference between confidence intervals and hypothesis tests. And we're going to see also another difference when we talk about two sample, but I'm just right now the difference that comes up with a single sample test on proportions is that our H0 provides us with a default value of probability of success, which we'll call P sub naught, that we assume is true until proven false. So this thing here allows us to compute the standard deviation of P hat. Using the assumed true probability of success P naught. So instead of, in the confidence interval, we had P hat Q hat over N because we didn't know the true value of P, so we used our estimate. Now in hypothesis tests, we're going to use the claimed value of probability of success P naught. So sigma P hat becomes square root of P naught Q naught over N. So just remember that one difference between what we're going to see here in the hypothesis tests and what we saw with confidence intervals. So let's illustrate this with an example. Let's suppose an official with the NCAA claims that only P equals 0.01, i.e. 1% of college football players use anabolic steroids. Others believe that P is greater than 0.01. And now let's suppose we've selected 17 players at random from a sample of 546 players, and these 17 players, we've selected 546 players and 17 of those tested positive to a steroid test. Then what is your conclusion regarding the official claim? You will use a significance level of alpha equals 0.005 and report a p-value. So we're choosing a fairly small significance value here. Since we're reporting a p-value, we'll see, whether we needed to choose a small alpha value like this. Okay, so we have to look at this statement. Others believe that p is greater than 0.1, and then we're given some information and said, what is your conclusion regarding the official claim? So I would say the official claim is that p is equal to 0.01. We're trying to prove that this is false. So we want to put in HA that P is greater than 0.01. Then if I reject the null, I can conclude that P is greater than 0.1 and that the official claim is incorrect at, in this case, a 99.5% confidence level. Okay, so that means I want to write this. H0 P equals 0.01 is the default claim, and HA P is greater than 0.01, and this is what we are trying to prove. This is the one-sided test, so we're going to be using alpha, not alpha by 2. We are told n is 546. The number of, I'll call it successes or people that tested positive amongst those 546 was 17. So our estimate of p hat is n sub n over n, which is 17 over 546, and that's 0.031. By the way, I'm sort of using I'm abusing the notation here. This capital N should really be random, and we actually have a realization of it here. So this should be little n sub n, but I find that's equally confusing, so I've left it as n, capital N sub n, but this is a realization of the actual random binomial distributed random variable. Okay, so we have p hat is 0.031, and our sentences, as usual, we reject h naught of our test statistic, and here we're plugging in the values that go into the various brackets. This is a test on proportions, so we're always going to be using z here. It's a test on a single proportion, so a test on p. So here we put the estimate of p, which is p hat. This is the mean of p according to the null, and we're assuming that that's the null is claiming that's 0.01, so we put 0.01 here. And underneath we put the standard deviation of whatever we put in here, which is p hat. We know everything on the right-hand side. P hat is 0.031. The null claim is 0.01. And the standard deviation of p hat is square root of p naught q naught over n. In this case, p naught is this 0.01. So I plug in all the numbers there. I get z is 4.96. This is a pretty large value. It basically means that our p hat is almost 5 standard deviations away from where it's claimed to be by the officials. Okay, so continuing our sentence, we reject h naught of our test statistic. Z equals 4.96 is, and the value here comes from our alternative, and it's the greater than sign there, so we put greater than. Then we're looking in the positive direction, so it's plus z, one-sided test, so it's alpha here. Alpha was 0.005, and if we look at our tables, that's 2.576, and this is this test statistic is bigger than 2.576, so we reject h naught and conclude with at least 99.5% confidence that the true proportion of players using anabolic steroids exceeds 1%. And we can just check to see how good this approximation is. If I multiply n, which is 546, times the claimed null proportion of successes, which is 1%, I get 546 times 0.01 is 5.46. This is bigger than 5. And of course, q is 0.995. So at the other end, is it 0.905? Yeah, 0.905. And times 546 is way bigger than 5. So it looks like our normal approximation is reasonable. The p-value is the probability that we see, if we were to repeat this experiment, that we'd see a test statistic at least this big in the direction of HA. HA is greater than, so I put the probability that Z is greater than 4.96. Yeah, and if I look in the tables, I see my normal distribution tables only go up to 4. Where I see probability that Z is greater than 4 is 1 minus phi of 4, 1 minus 0.9999, so 4968, which is a very small number, 0.000032. So our p-value is going to be less than this number here. I would guess it'd be 0.00002 or 1 or something like that. But they basically, because this is so small, it shows very strong support for the alternative that p is actually greater than 1%. In other words, we are very sure that the official claim is incorrect. Okay, another example, a fuel company claims that 1/5 of the homes in a certain city are heated by oil. Do we have reason to doubt this claim if in a random sample of 1,000 homes in the city it is found that 236 are heated by oil? And we'll use an alpha equals 0.01 significance level, so a 99% confidence level, and report a p-value. Okay, so a fuel company claims 1/5 of the homes in a certain city are heated by oil, and then we say, do we have reason to doubt this claim? So reason to doubt means that I would reject the claim if I'm far enough away in either direction. That would say give me reason to doubt the claim. So I would say this is going to be a two-sided test where the claim is 1/5 or that p is equal to 0.2. Let's see if that's what I did. Yes, okay. So if we want to be able to say yes to the do we have reason to doubt this claim, then we need to put that doubt into HA. So we must test H naught, p is equal to 0.2, HA, p is not equal to 0.2. You should not look at the results of the test before you decide on how to answer this question. Okay, so reason to doubt, we could get that if we're too far to the left or too far to the left, or too far to the right. So two-sided test. We are told that n is 1,000. And the number of successes in 1,000 homes was 236. So my p hat is 236 over 1,000, which is 0.236. Since this is a two-sided test, our proportions will be using z, and so two-sided, the critical value is z alpha by 2, which is z is 0.005. We were using, yes, okay, so half of this is 0.005, which from the bottom line of the t-distribution is 2.576. Since the null hypothesis is assumed true until proven false, the standard deviation of p hat is obtained by assuming that the true proportion is 0.2. So my sigma p hat is the square root of p naught q naught over n, which is 0.2 times 0.8 divided by 1,000, and the square root of that whole thing gives me 0.01265. So our sentence, as usual, proceeds as follows. We reject h naught of our test statistic. In this case, z is equal to p hat minus the claim under the null divided by the standard deviation of p hat, which is 0.236 minus 0.2 divided by 0.01265, which is 2.846, this is a two-sided test. Where's our test? Right? Not equal to is a two-sided test, so our words here is either less than minus z alpha by 2, which is minus 2.576, or greater than plus z alpha by 2, which is plus 2.576. We see that this is bigger than this, so we conclude with at least 99% confidence that p is not equal to 0.2, i.e. the company's claim is false. For the p-value, we have to look in both directions. This is a two-sided test, so we take this 2.846 as being a distance away either in the positive direction or in the negative direction. So the p-value is the probability that z is less than minus 2.846 or greater than plus 2.846. We're going to round this to 2 digits, so that's 2.85. It's going to be 2 times 1 minus 5, 2.85, which is 0.044, which is a pretty small number. Basically, any time we choose alpha to be bigger than this, we're going to reject h naught. So it shows pretty strong support for HA, that p is not equal to 0.2. Okay, then we can look at tests on differences between proportions. So now we want to look at, so now we're talking about two populations. We're going to be looking at tests on P1 minus P2. We saw this already in confidence intervals. We're again going to be making use of the normal approximation, and our test statistic will be Z. And this will be reasonable if NP and NQ are both greater than about 5 for both populations. If our null hypothesis is as follows, that H naught, that P1 is equal to P2, which translates into P1 minus P2 equals 0, this is usually what we're going to be testing, that the null is that they're the same and the alternative is that they're different in some way. If they are the same, assumed under the null, then our estimates of p hat 1 and p hat 2 are actually estimates of the unknown common probability of success. And we're going to basically pool then the set of observations to get an improved estimate of this unknown but equal probability of success. And so how do we pool the data? Basically, we just count up the total number of successes from population 1, add it to the total number of successes from population 2, and divide by the total number of trials, N1 plus N2. Okay, so this is again a difference from what we did with confidence intervals, where we had p hat 1, q hat 1 over n1 plus p hat 2, q hat 2 over n2. Now we're going to use a common p and p hat. So p hat and q hat from here for both terms. Okay, so instead of p hat 1 and q hat 1 and p hat 2 and q hat 2, we're just using p hat and q hat on both terms. So we can factor that out. And basically the variance of the difference between p hat 1 and p hat 2 becomes p hat q hat times 1 over n plus n1 plus 1 over n2. And so the standard deviation is the square root of that whole thing. Let's illustrate this with an example. Let's suppose two different types of injection molding machines are used to form plastic parts. A part is considered defective if it has excessive shrinkage or is discolored. Two random samples, each of size 300, are selected, and 15 defective parts are found in the sample from machine A, while 8 are found in the sample from machine B. So I've sampled 300 from A, 300 from B. I found 15 defectives from A and 8 defectives from B. Then the question is, can you conclude with 90% confidence the fraction of defectives differs between the two machines? Now, it doesn't say greater than or less than here. It says just do they differ. So this is going to be a two-sided test. Alpha is going to be equal to 0.1, and we're asked to report an approximate p-value. So I emphasize again that it's asked if they differ, so it's a two-sided test. We're going to assume that they don't differ as the null hypothesis, and the alternative is that they do differ. And we're going to actually test this. H naught is that the difference, P1 minus P2, is equal to 0. So that 0 is going to show up in our test statistic. And the alternative then is P1 minus P hat is not equal to 0. As mentioned, this is a two-sided test. Now we can plug in the bits and pieces that we're told. We're told we have 300 samples from each population. I could call these, instead of N1 or N2, I could call it NA and NB, but I just call it N1 and N2. So these are going to be, N1 is going to be A, and N2 is going to be B. So the number of defectives from machine A was 15, so our estimate of the probability of success for, success in this case being defectives, for machine A is 15 over 300, is 0.05. And for machine B is 0.02667. Okay, alpha we're told is 0.1. That's 90% confidence. Alpha is 0.1. Two-sided test, so Z alpha by 2 is Z of 0.05, which is 1.645. Under the null, the two proportions are equal, so we pool the data to get the total number of successes was 15 plus 8, or total number of defectives in this case, 15 plus 8, divided by the total number of trials, in this case was 600. So my p-hat, pooled p-hat, is 0.0383, which is somewhere in between these two results as expected. So that our standard deviation of p-hat 1 minus p-hat 2 is the square root of p-hat q-hat times 1 over n1 plus 1 over n2. Plug in the numbers, I get the standard deviation of this difference is 0.01567. Okay, so our sentence is as usual. We reject H naught of our test statistic. This is proportion, so it's always going to be Z. The first something is the difference in our two estimates. By the way, just because we pooled them here, the only reason we pooled them here is to compute this quantity underneath here. But we still need the two estimates, p hat 1 minus p hat 2, up here to measure the distance. So p hat 1 minus p hat 2 minus where it's assumed to be under the null, which is supposed to be 0. So I can plug in the numbers there. We already know what the standard deviation of p hat 1 minus p hat 2 is from this line here. And I get 1.489 as my test statistic. And then continuing my sentence is, this is a two-sided test, so it's either less than minus Z alpha by 2, which is minus 1.645, or greater than plus 1.645. And this number here is not greater than or less than, so we cannot conclude that the two machines are producing different proportions of defective parts with 90% confidence. This number here is is sort of close to this, so I might be able to conclude this with like an 80% confidence. We'll see that when we get to the p-value here. P-value is the probability that I see this in another test in the direction of HA. See a value at least as extreme as this in the direction of HA, which is in either direction. So the p-value is the probability that Z is less than minus 1.489 or greater than plus 1.489, which is 2 times the probability that it's greater than 1.489. And that probability there is just 1 minus 5, 1 point, I've rounded it off to 1.49. And I get a p-value here of 0.136. So I see what's the 1 minus that is 0.86. So I see that if I had an 86% confidence, I could have rejected H naught and concluded that the two machines are producing different proportions of defective parts. This is not a very large p-value, so it just indicates slight support for H naught. Okay, so the final test that we're going to look at is the test on the variance. As we saw for confidence interval, the test on the variance involves a completely different test statistic. Recall that this chi-squared term is n-1 sx squared divided by sigma x squared. So this will be the form of our test statistic now. And then this thing here is chi-squared distributed with n-1 degrees of freedom. So this is probably best illustrated with an example. Let's suppose that we take the following measurements of watt hours delivered by 9 samples of a particular type of laptop battery. And so I got 9 samples here, 1, 2, 3, 4, 5, 6, 7, 8, 9. And suppose also that standards are such that the standard deviation of the watt hours delivered by these batteries cannot exceed 5 watt hours. That standard deviation cannot exceed 5. Can you say that the standard are not being met with these batteries? Test at a 5% significance level and report a p-value. Well, let's first of all look at the data itself and compute the sample average, or the x-bar, and the sample standard deviation. So x-bar is the sum of these numbers divided by 9, which gives me 85 watt hours. But we're really more interested here in the sample, in the standard deviation, and in this case the sample standard deviation, to test to see whether we're exceeding 5 watt hours or not. So Sx squared is 1 over n-1 times the sum of the squared deviations. I plug in the numbers here, I get 41. So the sample standard deviation is 6.403. This exceeds the standard 5 watt hours, but it could just be due to natural variability. The next set of observations of 9 batteries might be 3 watt hours sample standard deviation. So basically, we have to, if we wish to answer the question being asked, then we need to make HA is that the standard deviation is greater than 5. If we reject H naught, then we can conclude this is true, and then we can say that the standards are not being met by these batteries. Then I could say the standards are not being met. Yes, okay. So we need to test the following. H naught sigma x is less than or equal to 5, and we're going to actually test using sigma x equal to 5. So we always use the equality in here, and then against the alternative that sigma x is greater than 5. So our sentence, as usual, is we reject H naught of our test statistic. In this case, chi squared is equal to n-1 s squared over sigma x squared. Sigma x squared is coming from our claim, H naught, which is 5. Sx squared, we computed up here, was 41. Or you can take the 6.403 and square it and stick it in here, multiply by n-1, which is 8, and I get 13.12. So we reject H naught of our test statistic. Chi squared equals 13.12 is, and now I look at HA greater than, and our critical region now is our chi comes from our chi squared distribution. This is a one-sided test, so the subscript is alpha. Number of degrees of freedom is n-1, so chi squared 0.05 of 8. Look in the chi squared table and we'll see that's 15.51. 13.12 is not greater than 15.51. So we cannot conclude that sigma x is greater than 5 with 95% confidence. Okay, this 6.403 is greater than 5, but it's not significantly greater than 5 with 95% confidence. The p-value, basically we're looking for, if we were to repeat this, that the chi-squared value would be greater than the one we computed in the direction of HA, which is greater than. So that's the probability that chi-squared with 8 degrees of freedom is greater than 13.12, and this is approximately equal to 0.1. So this shows lukewarm support for H naught. We could say that we are approximately 90% confident that H naught is wrong. So if I were to adjust this test to, instead of 95% confidence, I used a 10% significance level or 90% confidence, then I would have been able to reject H naught and conclude that the sigma x is bigger than 5. Okay, I think one more example. We're saying a soft drink machine is said to be out of control if the standard deviation of the dispensed drink volume exceeds 10 milliliters. Now let's suppose we take a sample of 25 drinks from this machine, and that sample has a sample standard deviation of 14 millimeters, which is bigger than this 10 millimeters. Does this indicate at a significant level of 0.05 that the machine is out of control? Okay, so we're told we've sampled 25 drinks, so n is 25, and from that sample we got a sample standard deviation of 14, and then our alpha is 0.05. If we wish to test if the machine is out of control, then we must test, we put in our alternative that sigma x is greater than 10. If we reject h naught, then we can say the machine is out of control and we got to go do something about it. So we reject h naught if our test statistic chi squared is equal to n minus 1 s squared over sigma squared. Now it's just plug in the numbers. N is 25, so minus 1 is 24. S squared we determined was 14. S is 14, so s squared is 14 squared. And then underneath here we've got the claim is 10, standard deviation is 10, so the variance is 10 squared. Plug in the numbers here, I get 47.04. Finishing our sentence, we reject h naught of our test statistic is, we look at HA, and the word here is greater than, this is one-sided test, so it's alpha, 0.05, 24 degrees of freedom, and this number is 36.42 from the chi-squared distribution. This 47 is bigger than this, so we conclude with at least 95% confidence that the machine is out of control and that the standard deviation is bigger than 10 millimeters, so we presumably have to go in and fix it. What is the p-value? P-value is that the probability that if I were to repeat this, I would see a test statistic at least as big as this in the direction of HA. So HA is greater than, so p-value is the probability that chi-squared with 24 degrees of freedom is bigger than 47.04. I see from the chi-squared distribution table that probably chi-squared is bigger than 45.56 is 0.005. So I'm going to guesstimate that the probability that it's bigger than 47 is a little bit less than this, and I'm going to say that's 0.004. And that then is my p-value, and that basically is showing pretty strong support for the alternative. And I think that concludes week 11 lectures. And so that finishes up the hypothesis testing part of this course. Next week is week 12, and that's the final week of this course, and we're going to look at linear regressions, and we're going to see that linear regression has a certain part where we're looking at how to get a line of best fit, but it also involves confidence intervals and hypothesis tests, so you'll be using those things again in the linear regression part of this course. Okay, thank you. I'll see you next week. Have a nice day.